Hello, everyone. A very warm greetings. This is the final presentation of the condensed matter physics course. So we will be seeing about the topic free electron Fermi gas. And I am Hephsiba Siju, currently pursuing my PhD in the Department of Physics.
Hello everyone, this is Boya Mallikarjuna. I'm doing my master's degree in the Department of Material Science and Engineering.
Now, so regarding the free electron Fermi gas, the very basic thing is to understand what is Fermi gas. Uh, After that, we'll be seeing about the electron theory. So, what is basically Fermi gas? So, it is a gas that consists of particles with half integral spin and obviously which obeys the Fermi Dirac statistics. So, Fermi gas is that it consists of the Fermi gas, which consists of non interacting particles, is called as the ideal Fermi gas. Now, the Fermi gas obviously include the electrons in metals and semiconductors, electrons in atoms with large atomic numbers, nucleons in heavy atomic nuclei, and gases consisting of quasi-particles with half integral spin. So this is the very basic idea of what is Fermi gas. And now coming to what is free electron gas model. So we can say in simple way that the free electron model is the simplest way to represent the electronic structure of material. According to this material, we can say that the valence electron of the constitute atoms of crystal becomes conduction electrons and they travel freely throughout the crystal. So we can say that we can understand many physical properties of metal, not only of the simple metals in terms of free electron model. The utility of free electron model is greatest for properties that depends essentially on the kinetic properties of conduction electrons. Now, we said that it is the simplest way to represent the electronic structure of the material. But although the free electron model is a great oversimplification of the reality, surprisingly, in many cases, it works pretty well so that it is able to describe many important properties of metal. According to this metal, the valence electron of the constitute atom of the crystal becomes conduction electron and travel freely through the crystal. Therefore, within this model, we neglect the interaction of conduction electrons with ions of lattice and interaction between the conduction electrons. Now, in this sense, we are talking about the free electron gas, right? So, there are certain principal differences between the free electron gas and the ordinary gas of molecules. So the very first and prior difference is that electrons are charged particles. In order to maintain the charge neutrality of the whole crystal, we need to include positive ions. This can be done within a jelly model, according to which the positive charge of ions is smeared out uniformly throughout a crystal. This positive background maintains the charge neutrality but does not exert any field on the electrons. Ions form a uniform jelly into which electrons move. This is the first property or the principal difference. The second one or the second important property of the free electron gas is that it should meet the Pauli exclusion principle, which in turns lead to an important consequence. Now, this is the schematic illustration of the free electron model. We can see this is the true potential and this is the model potential. This model works relatively well for the alkali metals such as the lithium, sodium, potassium, cesium, and rubidium. We would like to understand why electrons are only weakly scattered as they migrate through the metal. This model transfers the idea of electron orbitals in atoms into a macroscopic objects too. Thus, the fundamental behavior of a metal comes from the Pauli exclusion principle. For now, we will ignore the crystal lattice. By a free electron Fermi gas, we mean a gas of free electron subject to the Pauli principle. Now, for this concept, we will be basically seeing about different ideas surrounding the free electrons. The first and foremost thing we have to see is about the free electrons in one dimension. Later on, we will be seeing about the three dimension also. So, regarding the one dimension, the first thing we have to see is the energy levels in one dimension. For that, we are considering a free electron gas in one dimension, taking account of the quantum theory and also of the Pauli exclusion principle. So here, an electron of mass m is confined to the length L by the infinite barriers. We'll be seeing a detailed explanation in the later figures also. The wave function psi n of x of electron is a solution of this coordinate equation, which is h psi n into x equal to E n psi n of x. What we are doing is we are assuming the potential lies at zero, so that the Hamiltonian H includes only the kinetic energy. So that the equation becomes h psi n of x, which is equal to minus h cross square by 2m d square by dx square psi n of x, which will be equal to the final equation of En psi n of x. Now, here the En is the energy of electron in the orbit. Here we use the term orbital, which denotes a solution of the wave equation for the system only with one electron. So basically what happens is this allows to distinguish between an exact quantum state of wave equation of a system, which is n, interacting electrons, and an approximative quantum state, which we construct by assigning the n electrons to n different orbitals, where each orbital is a solution of wave equation for one electron, as we discussed earlier. We know that the orbital model is exact only if there is no interaction between the electrons. Now we are applying the boundary condition for the wave functions, which are psi n of 0 equal to 0, psi n of L, which is also equal to 0. This is imposed by the infinite potential energy barrier. Now they are satisfied if the wave function is sine-like with an integral number n of half wavelength between 0 and n. So we can say the wavelength is between 0 and n. We are making it into a fixed boundary condition with psi n equal to a sine of 2 pi by lambda n x, and L, which is the standing wave solution, L 2 pi by lambda n, which is equal to n pi. So here the L value, which is given by n into lambda n by 2. Here the k value is given as n pi by n. So after the solution, after substituting everything, we'll get En, which is equal to h cross square by 2m into n pi by L the whole square. So here, as I said earlier, En is the energy. Now, according to the Pauli exclusion principle, we know that no two electrons can have all quantum numbers identical. So, on that principle, here we can see in this figure, we see the energy in this axis and the quantum numbers here. So, first, three energy levels. These are the three energy levels, and the wave functions of the free electron of mass m is confined to the line L. The energy levels are labeled according to the quantum numbers 1, 2, and 3 here. The wavelength are indicated on the wave functions. The energy En of the level quantum number is given by this final equation. Now, we know that in a linear solid, the quantum numbers of conduction electron orbital are n and ms. N is the quantum numbers and m is the spin quantum number. N is the positive integer and magnetic momentum may be plus 1 by 2 or minus 1 by 2 according to the spin orientation. Now, a pair of orbitals labeled by the quantum number n can accommodate two electrons, one with spin up and one with spin down. If there are, to an example, if there are like 6 electrons, then in the ground state of the system, the filled orbitals can be seen in this table. So we can say the orbital n equal to 1, 2, and 3. So all these 1, 2, and 3, it's seen as the electron occupancy is fully occupied. So here we can see one up and down, and here the occupancy is 1. So for the orbital 1, 2, and 3, we can see it is fully occupied. But for the orbital 4, it is empty. That is, here it is denoted as 0. More than one orbital may have the same energy, of course, it's there. Now, the number of orbitals with the same energy is called as degeneracy. It is an important term here also. Now, if let NF denote the topmost filled energy level, where we start filling the levels from bottom, which is n is equal to 1, and then continue filling the higher level with electrons until all n electrons are accommodated. So it is convenient to suppose that n is an even number. The condition 2nf is equal to n determines the nf. The value n is for the uppermost filled level. Now we are taking the term which is the Fermi energy, which is EF. EF is defined as the energy of the topmost filled level in the ground state of the n electron system. So, with the previous equation, we know that n is equal to nf. We have it in the one dimension, right? So we are discussing about the one dimension. So we'll get this final equation, which is the Fermi energy EF is equal to h cross square by 2m into nf pi by L the whole square. So after substitution, we'll get like h cross square by 2m n pi by 2L the whole square. Now, we are taking the term of Fermi-Dirac distribution, which is the effect of temperature on Fermi-Dirac distribution. So we obviously know that the electrons are fermions. The ground state is the state of the n electron system at absolute 0. That is the reason that we are taking like 2 electrons can occupy a state, one with spin up and one with spin down, as we discussed earlier. The Fermi function Fe is the probability that a state at energy E is occupied. So, uh, if the kinetic energy of the electron gas is increased as the temperature is increases. So what happens is some energy levels are occupied when which are vacant at absolute 0. Here, the electrons obviously obey the Fermi-Dirac distribution, which gives the probability that an orbital at energy E will be occupied in an ideal electron gas at thermal equilibrium. So the Fermi function f of E becomes 1 by exponential of E minus mu by kBT plus 1. Here, the quantity mu is a function of the temperature like mu is to be chosen for the particular problem in such a way that the total number of the particles in the system comes out correctly. That is which is equal to n. Now at absolute 0, mu will be EF because the limit is from t to 0. So here we are considering it as the temperature T is equal to 0 Kelvin. An ideal Fermi gas is in the ground state, and the particles of the gas occupy all quantum states with energy up to maximum value, which depends on the gas density. And this maximum level is called as a Fermi level, which is EF. The quantum states with the energy is greater comparing to the EF are empty, such as a distribution of occupied and empty states corresponds to complete degeneracy of the Fermi gas. This is the ground state of an electron system at absolute zero. Now here we can see the Fermi-Dirac distribution at temperature which is greater than 0 Kelvin. So what happens is the Fermi-Dirac distribution uh, is at various labeled at various temperature for TF, which is equal to EF by KB, which is 50,000 Kelvin. The result applied to the gas in three dimensions. So this is how, so from one dimension, it applies to the three dimension. The total number of the particles is constant, independent of the temperature here. The chemical potential mu at each temperature may be read from the graph as the energy at which F is equal to 0.5. So this is a level of 0.5. Yes, now from the previous graph, we saw that it gives way to the three dimension. So we are obviously coming to the free electron gas in the three dimension. So discussing about that, the first thing that we have to consider is the free particle Schrodinger equation in the three dimension, which is X, Y, and Z. So we know that the free particle Schrodinger equation, which is H psi of n x y z is equal to minus H cross square by 2m, which is equal to dou square by dou x square plus dou square by dou y square plus dou square by dou z square into psi n of x, y, z. Now this is equal to E n psi n, the whole term will be x, y, z. If the electrons are confined to a cube of edge L, the solution is the standing wave. So what happens is, for the standing wave, it becomes psi n x y z equal to a sine n pi by L x into sine n pi by L y into sine n pi by L z. So here we can see that the nx, ny, and nz are the positive integers. Now coming to the next part, in many cases, it is convenient to introduce a periodic boundary condition as we did for the lattice vibration. The advantage of this description is that we assume that our crystal is infinite and disregard the influence of the other boundaries of the crystal on the solution. So here we require that our wave functions is periodic, that is in x, y, and z direction with period L. So that the psi into x plus L y z is equal to psi of x y z. So this is in condition for x coordinate. So the similar equation can be done for the y and z coordinates too. Obviously, after this, the solution of Schrodinger equation satisfies these boundary condition has the form of travel plane wave, which will become psi k r vector is equal to a exponential I k vector dot r vector. This provided that the component of wave vector k are determined from kx equal to pi n x by L, ky equal to pi n y by L, kx equal to pi n z by L. Here, the nx, ny, and nz values are positive or negative integers. But we saw in the previous equation that the nx, ny, nz are the positive integers. Here it is either positive or negative integers. Now, coming to the dispersion relation In case of the 3D, if we now substitute this equation, the previous with the previously derived equation, we obtain for the energies of the orbital with the wave vector k. So it is denoted as ek equal to h cross square by 2m kx square plus ky square plus kz square. So here the dispersion relation is given by ek equal to h cross square by 2m k square. So it's like the dispersion relation for the three dimension. Um, it can later lead to the Fermi energy in one dimension and three dimension. Uh, in the later slides, we'll be seeing about the next condition.
Now, I would like to explain about the density of states in 3D case. So, before that, you can observe in this figure, it shows the spherical shells in the three-dimensional case. And the K shows the wave vector, it has a different discrete values. So that the K space showing the values of K as a points. The number of allowed states is the number of these points contained in the shell of radius K and thickness dk. So the problem of finding the number of allowed states amounts to finding the number of these allowed states between the space and radius k and k plus dk. So k is where the k is radius and dk is the thickness. So in three dimension, value three in the three dimension, the value between two shells is given by dk vector is equals to dkx, dky, and dkz, which is equals to 4 pi k square dk. So now you can see here, now I would like to introduce the additional factor of to account for the intrinsic angular momentum of the electrons or spin states. The number of states is given simply by dividing this volume by volume of a single energy state. So that here you can see kx is equals to 2 by nx by L, ky is equals to 2 by ny by L, kz is equals to 2 by nz by L. So from that equation, there is a one quantum state within the momentum interval 2 by L whole cube. So that number of quantum states dn in the momentum interval dk is given by dn is equals to dk vector by 2 pi by L whole cube is equals to L by 2 pi whole cube dk vector, which is equals to L by 2 pi whole cube into 4 pi k square dk. So I want to multiply by 2 for a spin degeneracy. The number of states within the interval dk is given by. So already we know the dn. So 2 into, so we are now multiplying with 2, right? So 2 into L by 2 pi whole cube, 4 pi k square dk. So you can see here for the three-dimensional quantum case, we have E equals to h cross square k square by 2m and dk equals to m by 2 pi m by 2 s cross square E whole square into dE. So the density of the states per unit length in one dimensional, we have to multiply by 2 for spin degeneracy. So we will get dn is equals to 4 pi n into L by 2 pi whole cube. 2m by s cross square into a whole power 3 by 2 into 1 by 2 dE. So now we want to, for if you want for three dimension, the density of states per unit volume at energy E is given by density of states is equals to dn by dE is equals to 4 pi into L by 2 pi whole cube 2m by s cross square whole power 3 by 2 into e power 1 by 2. So you can observe in this figure, it shows the density of states of three-dimensional case. So here the density of states is directly proportional to the root of energy. So coming to Fermi energy in the 3D case, we already derived the DOS in the previous slide. You know that the density of states dn is equals to 4 pi into L by 2 pi whole cube into 2m by s cross square whole power 3 by 2 into e power 1 by 2 dE, which is already derived in the previous slide. So we want n, right? So I want to integrate the whole dn. So we will get L power cube by 3 pi square into 2m by s square and 3 by 2 into e power 3 by 2 f. Uh, After that integration, after that we will get Fermi energy, which is equals to h cross square by 2m into 3 pi square n by L cube whole power 2 by 3. which is equals to h cross squared by 2m into 3n pi whole square whole power 1 by 3 whole square. So in this, from the above equation, n is the electron density compared to the equation E equals to h cross square 2m into k square, which is leads to Fermi wave vector kf is equals to 3n pi square by whole power 1 by 3. So because the linear moment of an electron is p vector is equals to mv vector, which is equals to h cross k vector. So we derived the Fermi velocity of an electron as Vf is equals to h cross kf by m, which is equals to h cross m into 3 n pi square by pi square whole power 1 by 3. So here we can observe in this figure in the ground state of system of n free electrons, the occupied orbitals of the system fill a sphere of radius kf, where the ef is equals to h square kf square f by 2m is the energy of electron having a wave vector kf. And here is a Fermi's surface at energy ef. We can see the now we can discuss about heat capacity of a electron gas. So first of all, we have to discuss about the qualitative representation of electron specific heat. A major success of Fermi consideration of electron in metals, it could be explained that excess heat capacity in metals beyond that given by Conor's combines DOS and thermal distribution. So here I want to consider temperature T equals to 0, the Fermi direct distribution function drops precisely at T equals to EF. At a low temperature, the function remains roughly symmetric around the equals to EF. The number of electrons promoted is proportional to area between the T equals to 0. So that the finite temperature curves, which is directly proportional to T, and the average increases of their energy is also proportional to T. So the finite temperature system has a excess energy proportional to the T square. So the specific heat capacity is directly proportional to the temperature. So we can see, you can observe in this figures, so which indicates the Fermi direct distribution for various temperatures, where Tf is equals to F by Kb, which is equals to 50,000 kelvins. So this result is like at a gas in 3 dimensions, the chemical potential at each temperature is a value of 0.5 value. So in the above graph, that a specific heat is gradually increases directly proportional to the temperature compared to the figure A. So you can so you can see here the electrons near the Fermi surface are excited by thermal energy kT. The number of excited electrons is roughly ordered. N dash is approximately equals to n kT by kf ef. So the energy absorbed by the electrons is U is proportional to approximately is equals to n dash kT. We already derived the n value, right? So simply we can substitute in this equation. So we will get n kT square by ef. So therefore the specific heat capacity of electrons given by the following equation. Specific heat capacity of the electrons is equals to dou u by dou t, approximately which is equals to nk into t by tf. So in general, we know that for Fermi temperature is above 50,000 Kelvin. For example, classic thermodynamics, the specific heat of a particle is given by C classic is equals to dou u by dou t into 3 by 2 nk. So the electron heat of electrons is 2 order less than expected in classic thermodynamics, because T by Tf is approximately is equals to 0.01. Therefore, usually electron specific heat much smaller than phonon specific heat. In general, C is equals to C electron plus C photon, which is equals to delta T plus in A into T per cube. So coming to so Cl becomes more important at very low temperatures. So see specific electrons becomes more compared to more important at lower temperatures. So coming to now we can see experimental result of electron specific capacity. We expect the total specific heat to be in the form of C equals to, as we discussed previously, C equals to specific heat capacity of electrons plus photons, which is equals to delta T plus A into T cube, A into T cube. So I want to divide with T on both sides. So I will get CV by T which is equals to delta plus A into T square. So delta is a specific capacity of electrons, and AT square is a specific capacity of a phonons. So where the phonons terms, which is from the Debye model. So if we plot CV by T as a function of T square, the intercept which gives you a delta, which is the gradient, gives you A. So we can observe in these figures the gradient will gradually increases compared to this, and we can observe in the summer field results in the both figures, though this figure indicates the specific heat of the material potassium at low temperatures. Yeah, now you can see electrical conductivity and Ohm's law. So now I would like to introduce the momentum of a free electron is related to the wave vector by mv in equals to h cross. So now we would like to take electric field E and a magnetic field B. So the force is acting on an electron. So the Newton's second law of motion becomes the following equation. So before that, we know that Newton's second law, which is equals to mass into momentum into acceleration. So F is equals to mass into change in velocity by change in the time. So which is equals to I would like to I will substitute in this equation above equation. So I will get h cross dk by dt, which is equals to minus e into e plus 1 by c into v into v. This is the electrical conductivity, which is uh, Newton's second law of motion. After that, I will get this equation by using you know. So in the absence of collision, the Fermi sphere moves in k space at a uniform rate by constant applied electric field. Yeah. So before that, if you observe this both figures, the figure A shows the Fermi sphere encloses the occupied electron's orbital in k space. In the ground state of the electron, the net momentum approximately it will become zero, because for every orbital k there is an occupied orbital at k minus. So coming to the figure B, under the influence of a constant force F is acting for a time interval for a t. Every orbital has its k vector increased by delta k, which is equals to ft by h cross, which is equals to displacement of a whole orbit has its k vector. Yeah, I mean, which is completely displaced the whole Fermi spared by delta k. So now we can see I want to integrate the previous equation with a b, which is equals to 0 to obtain k function of t minus k of 0, which is equals to minus e power t by h cross. If the force F equals to minus e into e is applied at a time equals to 0 to an electron gas that fills the Fermi sphere center at the origin of k space, then at a later time, e is the sphere will be displaced to a new center at delta k equals to minus e et by h cross. So now, because of the collisions of electrons with the impurities, lattice imperfections, and phonons, the displacement sphere may be maintained in a steady state in an electric field. If the collision time tau, the displacement of the Fermi sphere in the steady state is given by the previous equation with t equals to tau. So the incremental velocity is p equals to delta k by m, which is equals to minus e into tau by m. If in a constant electric field E there are n electrons of charge Q equals to minus E per unit volume. So the electric current density is J is equals to n QV which is equals to ne squared tau by into e by m. This is a Ohm's law. So we know that Ohm's law at a constant temperature. So the electrical conductivity sigma is defined by J is equals to sigma E. So by the previous equation, we know that J equals to NQV. So now I will get sigma is equals to Ne square tau by M. So the electrical resistivity is defined as a reciprocal of the conductivity. So that the rho equals to M by Ne square tau. It is easy to understand the result for the conductivity of a Fermi gas. We expect the charge transported to be proportional to the charge densities because the factor E by M enters because the acceleration is given electrical field proportional to E, which is inversely proportional to mass M. The time tau describes the free time during which the field acts on the carrier. So closely, which is same result for the electrical conductivity is obtained for a classical Maxwellian gas of electrons as realized at low carrier concentration in many semiconductor problems. So
Basically, in this presentation, we have seen about the basic idea of what is Fermi gas and what is the free gas model. Basically, the thing that we saw is the free electrons in one dimension and also in the three dimension. So the one dimension effect of temperature paves way for the free electron gas in the three dimension. And the important factor that we saw is about the density of the state in three dimensional case, which give rise to the Fermi energy in 3D case. And also the important topic that we have also seen is regarding the heat capacity, because we always know about what is specific heat capacity in the general terms, but here it comes under the electron gas Fermi energy topic. So that is how we saw about the specific heat of the electron and also the electrical conductivity regarding to the free electron. Yes, so the whole content is taken from the book of Introduction to Solid State Physics from the 8th edition by Charles Gitter. Uh, yeah, so thank you for listening to our presentation. Hope you understood a very basic idea of what is Fermi energy, Fermi gas, and the free electron theory or the free electron Fermi gas theory. Yes, so thank you for your attention and hope to see you later. Bye bye.